I think as developers, we've come to accept this premise that working with AI is inherently going to produce low quality code, and that's basically inevitable. People seem to either accept this as a trade-off for the speed it allows them to ship new features, or they avoid using AI as much as possible for this exact reason. For the past 6 months, I went into the rabbit hole of trying out different approaches to address these quality issues, and ultimately ended up writing my own opinionated coding harness from scratch, which I called Teddy, and I just released the 0.1 version of it, and it's open source and available on GitHub. In this video, I want to take you through what inspired this project, how I thought about the core problems regarding code slop in general, and also in particular when it comes to working with AI, and how I approached trying to solve them. So in this video, we'll first break down how coding agents actually work under the hood, and what are the inherent limitations that LLMs have, which lead to two different types of quality issues, as we'll see. And looking into them, we'll see that these aren't issues that are specific only to working with coding agents, and that actually software engineers have had to deal with these long before the advent of large language models. Secondly, we'll look at the real-world software development practices that have inspired Teddy. And as we'll see, these methods are designed to, on one hand, prevent, and on the other, mitigate those two categories of issues. And we'll also see how we can make these work for coding agents as well. Lastly, we'll look at the technical design choices that make Teddy very different from other harnesses, and the reasoning behind those choices. As part of that, I'll also show you different ways you can use Teddy and how to integrate it into your own workflow and tailor your experience to your own preferences. So yeah, let's start. So if we look under the hood, an AI agent is really just a large language model paired with an external program called a harness. Since LLMs can only output text, they can't really edit files or run commands on their own. They need a middleman for this. So by structuring the responses in a specific format, the harness is able to interpret the LLM's output, execute the commands on your system, and then feed back the results to the model, closing the loop. Because of the way they are trained, LLMs have some intrinsic problems when it comes to real-world applications. So first and most obviously, they are primarily next token predictors, which are only later fine-tuned on relatively short, well-defined, and verifiable tasks. This makes them very narrow-sighted and unable to truly reason across long horizons or navigate fuzzy, open-ended problems. Additionally, LLMs are trained to jump straight to the final solution and try to guess it all at once, rather than using an iterative approach like humans learn to do. And unlike humans, LLMs have no internal skepticism, so they don't tend to stop and verify their own work. They usually just assume they're correct and keep going. This means even small mistakes, if left unchecked, will inevitably compound over time, given a long enough horizon. And this is where most agents fail. When you pair an unreliable LLM with a thin, unopinionated harness, which most of them are, the inevitable output will just be slop. Big Tech's answer to this equation has been to just throw bigger models with bigger context windows at the problem. That has surely improved the baseline performance, but it cannot fix the root issue. On a long enough horizon, mistakes are inevitable, and they will still compound over time. And we are increasingly hitting diminishing returns as well, with costs per token increasing faster than the actual improvements in performance. To hide this fact and secure their next rounds of funding, companies are increasingly focusing on benchmarking at the expense of transparency and real-world performance. That's why on the model front, I actually believe the future belongs to smaller, faster, and more efficient open source models, and why Teddy defaults to using DeepSeek V4 Flash right now instead of something like Claude. When properly harnessed, I do believe these lightweight models punch way above their weight class and for a fraction of the cost. Okay, so to figure out what we can actually do to fix this issue, we first need to understand what makes code slop in the first place. Because slop is not an LLM-specific problem at all. It's a fundamental software engineering problem which human developers have been struggling with long before LLMs were even a thing. So let's start by making the distinction between technical defects and misalignment issues. A technical defect is code that simply doesn't run or doesn't work as intended. This could be, for example, a typo, a forgotten import, or an unforeseen edge case. Misalignment, on the other hand, is what happens when the code itself does what it's meant to do, but completely misses the mark on what the user actually wants. To create high-quality products, software engineering needs to both, on one hand, prevent these issues upfront, and at the same time catch them as early as possible when they do happen. So while these issues are universal, they are also magnified when working with AI. So what most people do to try to solve these issues is bolting on additional systems onto their agents using things like MCPs, skill files, or spec-driven development. And while these approaches do have some merit, they fail to address the root of these problems and often lead to a fractured and frustrating development experience. So for example, skill files can help inject some domain knowledge into the agents, but it won't stop technical defects from compounding if the AI is still trying to one-shot the whole solution. And similarly, specs do prevent technical ambiguity, but miss the fact that misalignment isn't a technical issue, it's a design issue. And good designs emerge through iteration and cannot be planned all out in advance. So instead of trying to patch these existing approaches further, I wanted to instead take a page out of real software engineering practices, those that have been proven to work with humans, and build my own coding harness designed around them. Okay, so if we map our two dimensions, which we mentioned earlier, technical defects and misalignment issues, against the two strategies of preventing and mitigating them, we get this matrix where we can neatly place the core principles Teddy is built on. In general, for both of these types of issues, the root engineering challenge is to break the LLM's natural tendency to just one-shot the solution. So on the mitigation side, we need a framework that catches mistakes as early as possible by working in small verifiable steps. And on the prevention side, we must architect systems that make the correct solution the path of least resistance for the LLM. And we achieve this by adding constraints and removing ambiguity. So if we look at how to mitigate technical defects, as mentioned, we want to be working in small verifiable steps, and how we do that is through test-driven development. So how it works is that we start with this red phase where we first only focus on writing a failing test which fails as expected. And this is crucial to do because it ensures that the model in this case actually understands the system's interfaces and how it's supposed to behave before it even touches the implementation code. And only once the test fails in this predictable way, we proceed to the green phase where we write the minimal code to make the test pass, and then proceed to a refactoring step to clean up the design and any code smells without actually altering the functionality of the code itself. Also, in addition to this red-green refactor cycle, what I found working very well is to use commit hooks, which act as automated guardrails, so that if a test fails or a linter catches an issue in the code, the commit itself is blocked. And this safety net, this local safety net, is also meant to work alongside a remote CI/CD pipeline in order to allow you to work with the agents in parallel without worrying about integration later. Moving on to preventing technical defects, what we do is we add constraints using a design by contract methodology. So this means we codify the preconditions, post-conditions, and invariants of our components before any concrete implementation is written. In addition to this, we also adhere to an hexagonal architecture to isolate the core business logic from the external dependencies. And This makes it so that if the AI attempts to violate a contract, these native assertions we have implemented as part of design by contract will catch them. And while this doesn't guarantee the implementation is actually correct, it structurally makes the correct solution the path of least resistance. When it comes to preventing misalignment, our main focus is removing ambiguity. In order to do that, we employ the double diamond methodology, where we first focus on understanding the problem space, going through a phase of discovery, and then converging on a clear problem definition. And once the problem is well understood, we then proceed to explore the solution space. And we do this by developing and iterating on prototypes until we then converge on the best solution. Of course, this is a highly iterative process, so sometimes a prototype actually then changes our understanding of the core problem itself, and this sends us back to redefine our assumptions and proceed with another iteration. A key tool that we use throughout this process is the spike, which is a concept taken from extreme programming. And to explain it, Spike is a code that is developed rapidly, is meant to be highly explorative and disposable. So thrown away once the actual insights the code is supposed to deliver us are gathered. And by using these spikes and prototypes, we can validate both user expectations and the technical feasibility of our solution before writing the actual implementation of it. But even working with a prototype, we cannot account for the hidden complexities which only emerge once we start writing the production code. So to mitigate this during the implementation, we still need to work in small verifiable steps, and we do this using vertical slices. This means instead of building the system layer by layer, like writing the whole UI layer, then moving on to the logic, and then finally figuring out the data storage, we implement only what is needed for one feature at a time, end to end. A vertical slice is then also broken down into smaller independent deliverables that we implement and commit one at a time to ensure continuous integration. And at the end of every slice, the advantage is you get a fully working feature, which you can review and verify that it's aligned with your intentions before moving on to the next slice. All right, so let's look at how Teddy implements these principles in practice now. Yeah, so what you see here is the full workflow that Teddy employs. And don't get overwhelmed by the diagram itself. The concept behind it is actually pretty simple. So the core idea is that we split the development process into distinct agents and use Markdown documents as a way to mediate their interaction. And this also serves as a layer of abstraction for you as the user to steer the project at a high level. Now, using Markdown by itself is not a new idea when collaborating with AI. But what makes Teddy different is that the structure and lifecycle of each of these documents is designed to be the core around which each agent's workflow revolves around. Every section inside these documents plays a dedicated role in the process and is meant to be the anchor point that grounds each phase of the workflow and makes the process reliable and repeatable. As an example, I want to show you how a vertical slice document looks like, which is one of the most important documents inside of the Teddy workflow. So this is taken directly from the commit history of Teddy itself. So first of all, the documents, as you can see here, are committed alongside the code, so the document changes are committed alongside the code changes, which makes it very easy to keep track of the context of these changes. So looking at the structure of the document itself, you can see here we have some metadata, first of all, so where we have defined the milestone. These are other documents, the prototype, component documents, etc., which are useful for the developer to have in context. And we start with the business goal, and we define the overall goal of the slice, and then we define the different scenarios using user stories and jerking scenarios using given, when, then format. And below that, we define the edge cases that we want to account for. And before implementation, of course, you have a chance here to verify everything that you are aligned with everything that is written here. And after that, we have the heart of the document, which are the deliverables. So we break up the implementation of the feature into different deliverables. Yeah, and so after that, we also keep track, after the implementation of each of these deliverables, we also add the notes of what has changed. So the developer will add the changes that have been made to have as context, basically. Also keep in mind, you don't need to memorize this workflow to start using the harness. Teddy uses the Pathfinder agent by default, which will also guide you on which specialized agents to call next based on your needs. But of course, as you get more familiar with it, I think you'll naturally internalize this workflow and learn to use each agent as an independent tool. So I won't go into too much detail in this video on the individual roles of the agents here, but I might cover them in more detail in a future video if there is interest for it. Instead, let's now look under the hood to see how these agents are actually constructed. So we are right now inside a new project folder, and once I run teddy init, you will see a .teddy folder being created, and inside of it you will have the different agents inside of the prompts folder. So every agent is defined in a plain text XML file to make it as easy as possible to customize and fine-tune them. Looking at the developer agent here, we can see the workflow is broken down into different phases. So let me shortly collapse these so we can have an overview. So we have these 5 different phases: orientation, implementation, integration, documentation, and delivery. And each of these are broken down into steps. So if we look, for example, at the implementation phase, we have these red, green, and refactor steps, which we mentioned earlier being the core of test-driven development. In addition to these specialized agents, which we have shown in the diagram, we also have a more generic assistant agent, which is designed for those quick ad hoc tasks that don't fit inside of a structured workflow, and it behaves like a more traditional unopinionated coding agent, just basically following your instructions. And more importantly, the assistant agent is also meant to be used as a template. So by copying this agent and changing its workflow instruction, you can create your own custom agents. So how do you actually start using Teddy? So first of all, I should have mentioned, to install Teddy, you simply run pip install teddy-cli. And once you have done that, as mentioned, you can run teddy init to create the initial .teddy folder. Within that folder, you also have the configuration file, where you simply, to get started, you simply need to select your editor of choice. So in my case, I use Codium, and you can use here any editor that is configured in your path. And in addition to that, you then simply have to insert your API key. And the Teddy is compatible with any endpoint that is supported by Light LLM, which are most of them, and you can even use local models for that. I recommend starting out with OpenRouter just to test things out. And in particular, you can start by default, the model selected is DeepSeek V4 Flash, which is very cheap and can show you also how good these lightweight models can perform when properly harnessed. So once let me insert here the API key, and let's go with the general assistant agent for now. And you can also optionally add, first of all, any additional context files. So any files you want to pass to the agent as context using C. And you can also use the Y flag or YOLO to approve any actions directly. So let's just start with the assistant agents. And when you start, you will see there is a check for pre-commit hooks. So if these are not configured, you will get this warning. They are recommended to be used with Teddy. And also the Git repository will be either detected or initialized if not existent. Right, so then you can start. And for this case, let's create a simple snake game in Python. Oops, I misspelled Python. Once you start the session, you will see a new session folder will be created, and which you will see inside of .teddy. So inside of the sessions folder, you will have a subfolder for that specific session, and within each session, you will have each of the turns. So each turn, you will see you have the input file. So this is everything that the DI is given as input. So we will see we have system information and session history. So your initial request that, as you can see, I misspelled here. Git status, project structure, which right now is empty, and resource contents. So the files that are passed here, you can see them inside of each session. You have the session context. So these are all the files that are passed in context. And these are initialized starting from the init.context file, which starts out with these 3 default files. And you can add your own and add comments using the hash symbol. And exactly, so once you've done that, each turn, the AI generates a plan following what we call the Markdown response protocol. So this is a structured format that the AI has to follow to be compatible with the harness. And the important elements of this response format is that we have this title indicating what this turn will be about, a status which can either be on track, off track, or blocked, and which you will see in the terminal itself. So you will see the title and the status. And followed is a rationale that summarizes what has happened so far, the important information, and gives you context about the plan we are executing this turn, and also keeps track of the different phases of the workflow in the state dashboard, and keeps track of any pending actions. So you will see after that we have a message. So in this case, the LLM is asking us for feedback, and we can either reply directly here in the terminal or open using E in the editor. So let's do that. You will see you can provide here an answer to the question. Let's just say just create a simple proof of concept, and you can go also multi-line, of course. And once done, we confirm our reply. We get it summarized here in the terminal as well. And everything, this whole interaction, you can see will be also logged here inside of the session folder as part of the history log. And yeah, let's wait for it to do some actions. So yeah, we got a response back, as you saw. And the nice thing is this Markdown plan, being that it follows this structured output, can get directly parsed by the harness. So we will see here we have the different sections parsed, which make it easier to navigate and to review. And each of these actions can be individually reviewed and modified, and select or deselect certain actions that we want to execute. We can even go in and modify the details of it. So maybe let's go in and rename the file to snake new, for example. And we can also use E to modify the contents of the file itself. So we can go in and say comment and confirm with Y. And once we have done that, we can submit our plan. So let's say we want to execute all of these steps. We can press S to submit them. You will see the files have been created. So this is the actual file now, and it has the comment, and the renaming has also happened. And you will see we can the response gets sent back directly to the LLM. So we see here the report for the second turn. So we see the create action succeeded. The execute action actually failed. So we see we have here a error. So there is no snake.py. That's expected because we renamed the file actually. So now this report is sent back to the LLM, which produces a new plan. And as you can see, it reflects on this. The previous attempt created snake new. User modified the path, but then failed because the syntax check referenced snake.py, which didn't exist, etc., etc., etc. So now we get this new plan, which we can review, modify, etc. And also the cool thing is we can execute these actions also individually. So let's say we just want to execute this first action and then see what has happened. So we have executed it using X, and now I can go in with D and see the details of the action. So we see here syntax is okay. So I can go back and execute the next one, or I can also execute them out of order. And so let's say we can execute this one, and we see here this action failed because it's still referencing, I guess, the old file. But anyway, we can then go in, submit the actions that we want. Let's say we don't want to execute these other two actions, so we can submit it. And this report again will be produced. You will see the actions we skipped, the actions that failed, and this will get fed back to the LLM. So let's say we now break out of a session. So if I provide an empty response, I will break out of the session and I can resume the session anytime, as mentioned here, using teddy-resume, optionally passing the path, or if I don't provide anything, it will resume the last session. So I can go with teddy-resume and resume the session as it was. Okay, so another cool thing I want to show you is because everything is just plain text, you can actually use Teddy directly in your browser as well, so you're not limited to using the LLMs through the API. So what you can do, for example, is go in and copy one of the agent prompts. So let's say let's copy the assistant prompt as before. We can go in your browser, for example, here in Google AI Studio, but you can also use anything else, Claude or whatever. You can paste the system prompt. And now you can start using Teddy directly inside of your browser. So let's put it here to the side so I can show you how it's done. And we can instruct the AI with the same instructions as before. So let's first of all actually provide the context. So the same thing that happens directly in the CLI, we can do also here manually using Teddy context, which will also pull the file contents. Then we get this copied to the clipboard, and we can provide it to the LLM together with our instructions to create a simple snake game in Python, spelled correctly this time. And you will see we should get the same response format exactly, which we can then go in and execute directly. So in this case, it's just a message. So let's reply directly and say, as before, just create a simple proof of concept. And you see the Markdown response protocol is very well instructed. It's very well prompted in a way that also across models we have consistency in the responses. Okay, cool. So we see it is creating some files. Perfect. It's actually creating those documentation files as well, which we didn't ask for. But anyway, we can go in and do teddy execute to execute the plan directly from the clipboard. And you get the same view to review the action. So for example, we don't want these to be created. So we can just execute the actions that we want. And we can also attach a message to it. So this works both in this manual execution mode as well as in the CLI directly. So we can press M to add a message to it and say, just create the code and don't create any documentation. For example, come back, confirm it, and let's now submit this execution. And once we have executed it, we get the execution report back, and we can submit it again here, and you will see the message that we provided. Perfect. All right, so I think that will be it for this video. I just wanted to mention you can check out also the source code for Teddy. It's fully open source under the AGPL license, so you can use Teddy however you want. It will always be open source like that. And I've been dogfooding this workflow over the last 6 months, building actually Teddy itself, and it has changed completely how I collaborate with AI. The GitHub link will be down in the description, and I would love you to test it out on your own projects and share your feedback with me. That would be very useful. And if you could also drop a star on the repository if you enjoyed the project, that would be also great. If I see there is interest as well on this video, I'll also go deeper in future videos about how to use specific agents and in specific situations, and how maybe each of them works more in detail. So yeah, for now, thanks for watching, and I'll see you in the next one.